Hey everybody, welcome to class 105. This is also going to be lab 25. A little bit more on that on the next page. So our goal for today is to describe how charge and distance affect the electrostatic force between two objects and to derive Coulomb's law. So thinking back to the first quarter, what's Newton's first law? So Newton's first law, it can be put a bunch of ways. Some people say an object in motion stays in motion, object at rest stay at rest. So we can, write down a more formal definition of it. Unless acted upon by an outside force, right? That's the most important part. So an object in motion will remain in motion in a straight line an object at rest, didn't really give enough room here, will remain at rest unless acted on by a net force, F net. Okay, so a net force is required to move objects. So think back to earlier this week. What happens when you bring a charged object near another charged object? So they're going to either attract or repel, i.e., they're going to move. Therefore, a force must exist between the two objects. In order to make things move, you need a force. Okay, and what is that force? That's the electrostatic force. And Newton's third law tells us that the balloons attracted the piece of paper, but the pieces of paper also attracted the balloons. If you recall from earlier in the week, the balloons picking up the paper. All right. So this lab is going to use a simulation. It's the best we can do in these circumstances. So click on the link. I'll try to put a link in the description if I remember. It's called, it's a PhET simulation. It's called Coulomb's law. All right. So when you open it up, play with the simulation for a minute or two just to see how it works, and make sure you pick macro scale. All right. All right. So if we open up the simulation, I have the app, so I can just use it there. All right, so just looking at this, a few things. We can move these guys around. All right, we can move them left and right. Notice how the force acting on the charges changes. Okay. Notice Q1 and Q2. That's what we use for charge in physics. Q is charge. Just like M is mass, Q is charge. On the bottom, we can change the amount of charge. It's measured in microcoulombs. That's times 10 to the negative 6th. Positive charge, negative charge. Notice when the charges are opposite, they attract. When the charges are the same, they repel. We have the force values up there and measured in newtons. We can move the objects farther and closer. If you notice here, that one's at the 0 centimeter mark, Q1, and I could put this one, Q2, at, for example, the 2 centimeter mark. So they're 2 centimeters apart. Okay, when we measure the distances, we always measure from the center of one to the center of the other. That's why this one is, these are 2 centimeters apart. All right, so once you get the feel for that, go back to the class notes and let's start working through it. So you can probably do these on your own. We've actually done a lab just like this way earlier in the year. I think it was like class 48. So if you look back to that, you can probably do this on your own almost. And I would encourage you to try to do as much of this as you can without watching me in the video go through it. But I'll go through the answers. Just make sure you actually do these things on your own. So move the charges back and forth. How does distance affect the electrostatic force? If they're closer, looks like the force gets bigger. If they're farther, looks like the force gets smaller. Okay, so closer, force goes up. farther, force goes down. Now that makes sense to us. That should be intuitive, that farther apart, less force. What do you notice about the magnitude and direction of the electrostatic force on Q1 as compared to the electrostatic force on Q2? So if we look right now, notice that both charges feel the exact same force, but look at the direction. They're in opposite directions, right? Now what if I made one the other way, one negative? Well, the magnitude is still the same, and the directions are still opposite. Now they're just pointing towards each other. So magnitude is the same, opposite direction. Equal magnitude, opposite direction. And that's what Newton's third law tells us, that the forces that come in pairs will be equal in magnitude and opposite in direction. So now we're going to take some data. So make sure you can do this data on your own. So it says set the distance between the charges to 2 centimeters apart, and then record the forces. All right. It actually doesn't matter what you make the charge itself. We'll keep that easy though. We'll make the charges like 1 and 1, just to keep it simple. Don't make either of them 0 though. All right. So put this one here. We'll put this one at 2. All right. It's kind of hard to get it exactly at 2. All right. So when they're 2 centimeters apart, the force between them is 22.469. So record that. Now, if you chose different charges, your number's going to be different. That's fine. You can still, it'll still work. All right, so let's go 3 centimeters apart. 9.986. Four centimeters apart. 5.617. This is all measured in newtons. And the reason it's measured in newtons is because it's still force. Okay, all forces are measured in newtons. If we go to 5, 3.595. If we go to 6, 2.497. And if we go all the way to 8, we're skipping 1. 1.404. All right. So just double checking all this, but it looks good. All right. So let's answer some questions now. This part with the graph here on the right, we'll come back to that in a moment. So it says, how does the electrostatic force change? So Fe means electrostatic force, force electrostatic. How does it change when the distance increases? So as distance gets bigger, distance up, force goes down. And we mentioned that earlier. What about when the distance decreases? Well, as the distance decreases, the force goes up. Why would we call this an inverse relationship? Well, the reason being is one goes up, the other goes down. So let's see. How does the electrostatic force change if you double the distance between objects? So let's look at an example. Why don't we take 2 and 4? That would be an example of doubling, right? Going from 2 to 4. How did the force change? So what I would do is well, we're going to look at the ratio, right? Did it double the force? Did it get cut in half? To figure that out, we can just put 5.617 divided by 22.469. All right, if you throw that in your calculator, let's see what we get. We get almost exactly 0.25. So it gets quartered. What happens if you triple the distance? So we have some options here. Actually, I don't know if we have options. I think we only have one. We can compare 2 centimeters to 6 centimeters. So again, I'm going to do 2.497 divided by 22.469. And we get 0.111 repeating, or it's 1/9. So if we double the distance, it's quartered. If we triple the distance, it's 1/9 as strong. Well, what happens if you quadruple the distance? So in that case, that would be like 2 and 8. All right, and you can do that one on your own. And what you'll see is if you quadruple the distance, it ends up being 1/16. But check that out on your own. Compare the two and see if it ends up being essentially 1/16. So this isn't a normal inverse relationship. Okay, a normal inverse relationship would be if you double the distance, the force gets cut in half. But in this case, if you double the distance, the force gets quartered. So this is an inverse square relationship. Okay, so our friend Coulomb, he's the guy that came up with this. That's why we named the unit of charge after him. Coulomb concluded that the electrostatic force was proportional to, we're going to use r squared. So this, by the way, means proportional. Okay, to r squared. What does r mean? R is the distance between them, specifically the distance between their centers. All right. So here's a sample question from an old exam. An electrical force of 8 times 10 to the negative 5 newtons exists between 2 point charges, Q1 and Q2. Again, we use Q to signify charge. If the distance between the charges is doubled, the new force will be, well, we just established that if you double the distance, you get 1/4 the force. So we basically take that original force and divide it by 4. So 8 times 10 to the negative 5 newtons divided by 4, we get 2 times 10 to the negative 5 newtons. So now we're going to see how the amount of charge affects it. So we just looked at how distance affected it. Now we're going to look at the amount of charge. So how did the charges of the two objects affect the electrostatic force between them? So change the charges without changing the distance between them. How does the charge affect the electrostatic force? So let's see, we'll set the distance, just leave it right there. So let's play with the charges. So as I make the charge bigger, the force goes up. If I make the charge smaller, the force goes down. Notice though that negative also creates a bigger charge. So all that matters is that the absolute value of the charge. Okay? Positive or negative tells us direction for the charge. You know, if the two charges are both positive, it's going to be a repelling force. If one's positive and one's negative, it's going to be an attractive force, but of the same magnitude. So as charge goes up, remember Q is charge, force goes up. Okay? More importantly, the absolute value of the charge is all that matters. So set each charge to 1 microcoulomb and set the distance to 4 centimeters apart. Okay. And now we're going to take some data here. Now, don't worry so much about the units here. The units right here specifically can be a little confusing, but don't focus on those. We're just going to focus on the product of the masses. So the product of the masses, that part's easy. 1, 2, 3, 4, and 8. But let's get the forces. Now, I actually left this accidentally as force of gravity. That should be electrostatic force. And that shouldn't be the product of the masses. That should be the product of the charges. The reason I made that mistake is because I actually took this. This is right from when we derived Newton's universal law of gravitation. All right. Actually, I forgot to do something earlier on. Go back to the previous page. So just one thing about this. What I wanted you to draw here for graph was distance here on the bottom, electrostatic force here, And just to show that an inverse square relationship looks something like that. All right, so make sure you go back and do that. I'm going to be looking for that. All right, so to fill in our forces, let's see. So 1 and 1, the electrostatic force in that case was 5.617. All right, so we're going to make one of them 2, Q1 specifically. So it's 11.234. All right, Q1's now going to be 3. 16.852. We're going to make them 2 and 2 now. 22.469. And the last one, we're going to do 4 and 2. All right, so we're going to get 44.938. All right. So how does increasing the charge affect the electrostatic force? So obviously as charge gets bigger, electrostatic force gets bigger. And as charge gets smaller, electrostatic force gets smaller. What do we call this relationship, or why do we call this a direct relationship? As one goes up, so does the other. So what happens to the electrostatic force when you double one charge? So that would be like going from here to here, right? You're only doubling one of the charges in that case. And you could tell right there from 5.6 to 11.2 that the charge, or that the force doubled. All right. And what happens if you double both charges? Well, that would be like if you looked at, for example, going from here to here, you're doubling both charges. And there you could tell without doing math, electrostatic force quadrupled. Okay. So this isn't just a direct relationship. It's a linear relationship. Looks something like this. If we have force here and charge here, goes up something like that. All right. And just notice that it's actually proportional to the product of the two. So notice for number 25 here, when you double one charge, okay, when you double one charge, like here, the product of the charges was doubled. If you look at the next one, number 26, when you doubled both charges, the product of the charges was doubled. So, or excuse me, the product of the charges was quadrupled. So that's why the force was quadrupled. So it's actually proportional to the product of the two charges. So Coulomb concluded that the electrostatic force was proportional to Q1 times Q2. Okay. Looking at this question here, an electrostatic force of 5 times 10 to the negative 7 newtons exists between 2 point charges, Q1 and Q2. If Q1 is doubled, what is the new electrostatic force between the 2 point charges? So it's proportional to the product. So we're only changing one of them. We're only doubling one charge. So we're going to double the electrostatic force between them. So 5 times 10 to the negative 7 newtons times 2 gives us 1 times 10 to the negative 6 newtons. Okay? And he was able to come up with Coulomb's law. He came up with the electrostatic force is equal to Q1 times Q2 over R squared, combining those two things that we just derived. Now, there was also a constant, just like with the law of gravitation, there was big G, that was just a constant. There's also a constant for Coulomb's law. It's a lowercase k. All right? We'll talk more about what that is tomorrow. So the two big takeaways here, as charge goes up, force goes up linearly. And as distance goes up, we call it R distance, just like with gravitational force. Force goes down inverse square. So all you're going to be submitting for this class, because it's going to count as a lab, so it's going to count towards our lab requirement. All you're going to need for this class is to upload this page here. So your name's on top there, it says Lab 25, and this page here, so 2 pictures. If you didn't print this out, that's okay, but I'm going to need the answers written for all of these and numbered. So you're going to have like number 7, closer, force goes up, farther, force goes down. Okay? And for good measure, it wouldn't be a bad idea for all these. I should have done this earlier, but electrostatic force in particular, right? Because we're not talking about gravitational force. We're talking about the electrostatic force. All right. So, again, no questions to answer. You're still doing a Google form. You're submitting this in the Google form. Okay, I'll go in and grade it manually and enter the grade. But make sure I only get these 2 pages. Don't give me this first page. I don't want that. Just this page and this page. Again, you can take a picture. That's fine. Or if you edited it, you can upload that.